When an engineer programs a robotic arm to execute a weld, they're relying on task-space Cartesian motion planning. The end effector must follow a prescribed path in three-dimensional space, where its exact location is explicitly defined as a function of time. Computing the position along that path is a trivial exercise. 3D translation coordinates exist entirely within a flat Euclidean space, known as R3. To move from point A to point B, you simply draw a straight line and apply linear math to interpolate the coordinates. The paradox emerges when we try to interpolate the tool's rotation along that same path. If you apply straight-line linear math to robotic orientation, the system experiences a catastrophic failure. This happens because orientation does not live in flat space. It exists on a highly curved, non-Euclidean mathematical manifold, known as the special orthogonal group, or SO3. Failing to respect the topological curvature of the SO3 manifold means the math no longer represents a valid physical rotation. The hardware receives corrupted commands, resulting in coordinate frames that skew, warp, and trigger erratic, uncontrollable joint actuation. To understand this failure, we have to look at the standard 3x3 rotation matrix. The naive approach to motion planning takes a start matrix and an end matrix and simply blends their entries linearly over time. This animation illustrates the mathematical reality of that operation. Linear blending violates the strict rule that the transpose of the matrix multiplied by the original matrix must equal the identity matrix. As a result, the matrix loses its orthogonality. It falls completely off the SO3 manifold, and the physical coordinate frame becomes skewed and scaled, a meaningless state for a physical robot. To avoid dealing with matrix calculation errors, engineers frequently decouple the orientation into roll, pitch, and yaw, also known as Euler angles. They then apply independent linear interpolation to each variable. But Euler angles carry a fatal mathematical singularity called Gimbal lock. If the robot's pitch reaches precisely positive or negative 90 degrees, the yaw and roll axes perfectly align. The system loses one entire degree of spatial freedom, paralyzing the actuator. Even outside of Gimbal lock, independent Euler interpolation produces severe physical anomalies. You get wraparound errors, where interpolating from 350 degrees to 10 degrees forces the robot to swing a massive 340-degree arc instead of the direct 20-degree path. The angular velocity also becomes highly inconsistent along the route. Linear matrices violate the laws of physical rotation, and Euler angles produce unpredictable hardware trajectories. Reliable 3D spatial planning requires abandoning these structures for a representation that actually mirrors the curvature of space. The solution adopted across the robotics industry is the Unit Quaternion. This is a mathematical object that safely maps the curved SO3 space onto the surface of a four-dimensional unit sphere, labeled S3. This diagram shows a complex 3D rotation matrix collapsing into a single clean coordinate point on the S3 sphere. The equation governing this is the Quaternion formula. Q equals the cosine of theta over 2 plus the sine of theta over 2 multiplied by a unit axis vector. It condenses the exact same positional data into just four parameters, W, X, Y, and Z. Because it sheds the redundant values of a 9-cell matrix, the math operates efficiently without ever generating a singularity. There is one critical rule, the double cover constraint of SO3. In Quaternion math, the value q and negative q map to the exact same physical rotation. The sphere effectively maps every rotation twice. By routing commands through this four-dimensional mapping, trajectory planners gain a compact foundation that entirely eliminates gimbal lock. Look at this visual of two Quaternion points on our unit sphere. If we apply standard linear interpolation, known as SLERP, we are cutting a straight secant line through the empty 4D space inside the sphere, then pushing those points back up to the surface. This overlaid graph highlights the physical flaw of SLERP. Because the straight line distances don't map evenly to the curved surface, the angular velocity profile forms a steep bell curve. The robot is forced to speed up drastically at the midpoint of its motion and slow down at the ends. We correct this using spherical linear interpolation, or SLERP. Instead of cutting through the center, SLERP traces the true geodesic path, a great circle arc directly along the exterior surface of the sphere. Contrast the new velocity graph with the LERP profile. The SLERP calculation delivers a perfectly flat horizontal line, verifying mathematically uniform motor speed across the entire rotation. To execute this in an active pipeline, the algorithm first computes the dot product of the start and end quaternions. If that product is negative, the algorithm negates the end value. This handles the double cover rule, ensuring the robot takes the shortest geometric arc instead of spinning the long way around. The algorithm extracts the half angle between the orientations, represented by omega, using an arc cosine function. That angle is fed into the final SLERP formula, which applies a sine-based weighting to smoothly blend the start and end values. SLERP successfully executes two-pose interpolation. It guarantees the absolute shortest rotational distance while maintaining a constant velocity in the physical hardware. SLERP operates perfectly between two isolated points, but if a task requires motion through a continuous sequence of waypoints, chaining standard SLERP segments together creates sharp C0 continuous corners at every single node. These sharp angular discontinuities translate into infinite acceleration spikes. As the machine tries to instantly snap to a new velocity vector, it generates severe mechanical torque, damaging the joint motors and degrading the hardware over time. To maintain velocity and acceleration continuity across multiple waypoints, planners upgrade to SQUAD, the spherical cubic spline algorithm. This elevates the path to C2 continuity. This path animation demonstrates how SQUAD functions as the SO3 equivalent of cubic Bezier splines. It removes the jagged linear segments, bending the trajectory into smooth, flowing curves that still intercept the target nodes. It achieves this by calculating inner control points, denoted as S sub I. The math dynamically blends nested SLERP operations to create entry and exit vectors at each waypoint, rounding off the angular velocity curves. SQUAD is a strict requirement for multi-pose spatial trajectories. Bounding the rate of acceleration, the jerk, is what protects physical hardware from mechanical failure during complex operations. The math is perfectly planned, but physical motors cannot process Cartesian spatial poses. They only understand individual joint angles. We have to translate our idealized spatial path into actionable hardware commands. This requires differential kinematics. We need a mechanism to convert the Cartesian trajectory, operating in the SE3 matrix space, into precise localized velocities for every independent joint on the robot. The spatial twist vector, combining linear and angular velocity, is processed through the Jacobian matrix, mapping exactly how fast each joint must move. To calculate these unknown joint velocities, resolved rate control applies the Moore-Penrose pseudo-inverse of the Jacobian to solve for the motors. The Jacobian serves as the dynamic bridge. It takes the mathematical perfection of the SO3 spatial plan and converts it directly into voltage and torque. There is a final hazard during Cartesian execution: kinematic boundary and inferior singularities. These occur when physical joints align in a way that strips the robot of its ability to move in a specific direction. This heat map shows the manipulability measure. As the Jacobian's determinant approaches zero, the workspace collapses. Pseudo-inverse calculations attempt dividing by zero, demanding impossible motor velocities. Controllers intercept this using damped least squares, injecting a damping factor, lambda, to stabilize the matrix and clamp velocities safely. We represent orientations strictly through Unit Quaternions. We calculate precise, uniform paths using SLERP and SQUAD, and we drive the mechanical hardware using pseudo-inverse Jacobian control. Calculating flawless spatial motion requires more than linear approximations. It requires abandoning the flat space geometry of human intuition and engineering directly within the topological curvature of the SO3 manifold.